Okay, we are continuing on here. We started talking about balancing equations and reactions in general. And when we do see a chemical equation, we have our reactants, which are our starting material on the left-hand side of the arrow. We have our products, which are what is formed as a result of the reaction there on the right-hand side of the arrow. Remember, as we also talked about, there's some other things that we commonly will see in chemical equations. Again, up on top of the arrow, sometimes we may see symbols like a delta symbol, which usually means heat. Sometimes catalysts, which again are not reactants. They're not products. They don't get used up in the reaction, but they're usually there just to sort of facilitate the reaction occurring faster. So sometimes you'll see things like perhaps a metal like platinum. You may even see like an H plus, which is an acid as a catalyst and so forth. In addition, the states of our reactants and products are usually given as well when we look at the formulas for them. We talked about that when we do have an equation, it always should be balanced. And that's the idea of sort of the conservation of mass. Remember that when we do have a chemical reaction, really the only thing that's happening is we're breaking bonds. And we're breaking bonds on the reactant side. We're reforming new bonds on the product side. And that pretty much is only involving electrons. And since it only involves electrons, doesn't involve any type of protons or anything in the nucleus in a normal chemical reaction, we never change really the elements that we start with. So we always start with a certain number of elements. We end with the same number of elements on the product side of the reaction, but they may again be in different substances, compounds, formulas. But again, if we started with 4 carbons, we should end with 4 carbons. And that's the idea. Also, a reminder that when we do balance an equation, we only change the coefficients. So the coefficients are, again, the numbers that come in front of everybody. That is the only thing that we could do to balance an equation. We never change any of the subscripts in an actual formula because, again, that will change what that is. We never put any big numbers or anything like that in between. When we balance an equation, as we sort of talked about, sometimes it's really helpful to make like a table of all your elements on your reactants and product sides. It oftentimes will sort of point you maybe in the sort of correct direction in terms of balancing. Personally, I like to start with what is sort of the easiest to balance up front. That's usually a pretty good approach. Things that are really complicated in the sense of elements in multiple sort of substances on one side and like maybe one on the other side, save those for the end. So that's usually a pretty good approach. When it's all said and done, all the coefficients again has to be whole numbers. And it does need to be, again, the simplest set of whole numbers to be properly balanced. So once again, if you had a 4, a 2, and an 8, we can come back through and divide everybody by 2 and still get whole numbers. You would want to do that to have a properly balanced equation. We also saw an example that it is sometimes possible and maybe necessary to use a fraction, for example, to balance an equation. And you absolutely could use a fraction, but you do need to clear it when it's all said and done by multiplying by the denominator to have a properly balanced equation. Typically, if you need to kind of use a fraction, the general rule is the number you need goes up on top, and this number should match the subscript that's probably in the formula next to it. And that's usually the general sort of rule of picking the proper sort of fraction. Any questions on that there? All right, so we're in the middle of some examples of balancing. So let's continue our balancing journey here. So why don't you balance this one and I'll get rid of everything that I scribbled on this post. There we go. Okay, so let's take a look. Once again, I'm going to make like a little table of reactant and product side and my elements here involved. Do a little counting. I got 3 carbons on the left, 1 on the right. I got 8 hydrogens on the left and 2 on the right. I got 2 oxygens on the left. And again, here I do have 2 there plus 1 more there. which gives me 3. So again, nothing much balanced here. I'm going to go with what seems to be perhaps the easiest to do, and that would be perhaps the carbon. And we could do that by putting a 3 there in front of the CO2. That is going to, again, distribute to both things behind it. So that will give me 3 carbons. Hydrogens on the right there are still 2. And oxygen now I do have 6 here. 3 times 2 plus 1 more here is going to be 7. At this point, I have a choice between hydrogen and oxygen. I'm personally going to go with hydrogen as it's only in one thing on each side. So that makes it a little bit easier to balance. So to do that, I'm going to put a 4 in front of the hydrogen. And when I do that, I got 3 carbons. 4 times 2 is 8 for the hydrogens. Now on the first one here, I got 6 for the oxygens, and 4 times 1 is 4, which gives me 10. Now I can see I left kind of the oxygen for the end because it's in one thing on the left and 2 things on the right. So again, that makes it a little bit easier to leave for the end. And here I'm going to put a 5 to do that. Going to give me 3, 8, and obviously 5 times 2 is 10. Any questions on that there? All right, so let's take a look at a few more here. Then, all right, why don't you balance up this guy here and see what you end up with? And although I did sort of give you the formula up front, a reminder that if you are given something like this, again, all in words, the first thing that you want to do is make sure you get the correct formulas. So diboron trioxide, that's a type 3, so that's some prefixes. So we have our B2O3, reacts with water, which is H2O, and boric acid, which is BOH3. Remember that you do want to put the formulas down first correctly, just like you did, say, the nomenclature and wrote formulas. And then you want to do the balancing part. Again, very, very common people screw up by trying to do both of those things together, sort of write the formulas and balance at the same time. And again, you usually will end up with the wrong formula and have a really hard time balancing in that case. So always get the right formulas first before you even worry about the balancing. And then you should come back with the coefficients and balance. So we'll do our little table here. We got B, and O, and an H, looks like. So we got 2 B's there, 1 on the right. Oxygen, we have 3 there, plus 1 more there, which is 4. This 3 does get distributed to everybody inside the parentheses here. So we would have 3 oxygens. On the, bless you, on the left-hand side, we have 2 hydrogens. And again, distributing that 3 in there will give us 3. There's really not a lot to work with here since on the right-hand side, everybody's together. So easiest thing to fix is the boron, and that's probably a good place to start. So we're going to start with the 2. That's going to give me 2 boron. By the way, this also goes to everybody behind it as well. So when we look at our oxygen, we have 3 times 1, which is 3, also times 2 in the front. That gives us 6. And also for the hydrogen, 3 times 1 is 3 coming in. And then also multiplying it by that 2 will give us 6 as well. So again, parentheses, subscript on the outside goes to everybody inside. If you put a coefficient in the front, it also goes to everybody on the outside there in parentheses as well. So at this point, we obviously can't do anything with the right-hand side, so we do need to go to the left-hand side here to fix it. I am again going to go with hydrogen here because when I look on the left-hand side, I do see oxygen in 2 things. So it's just going to be easier to kind of fix the hydrogen. It's only in one thing on the left. So that is why I would choose hydrogen here. And to fix hydrogen, I could simply put a 3 there. And when I do that, I have 2 borons. Oxygen, I have 3 here. And this 3, once again, also goes to the oxygen there. And that is 3 and 3, which is 6. And that gives me 6. And that actually balances for me. And that's very common what happens when you balance equations. Sometimes at some point, you just put a coefficient. Maybe it fixes more than one thing that's unbalanced in this case. Any questions on that there? All right, try one more here or a couple more here. All right, balance this one up and see what you come up with here. All right, so let's take a look. So once again, here we're going to make a table. See what we got working with here. We got nitrogen, hydrogen, oxygen. Left-hand side, we got one nitrogen. Right-hand side, we got one, so that's good. Hydrogen on the left there, we got three, and on the right, we got two. And oxygen on the left, we have two, and on the right, we do have two, one in each of those guys. So actually, everything's balanced here except for hydrogen. In this case, we actually need 6 to kind of balance it. So we actually need to put a coefficient on both sides. So to get my hydrogen on the right to a 6, I will need a 3. Get my hydrogen to a 6 on the left there, I will need a 2. That's going to give me 2 nitrogens on the left. 3 times 2 is 6, and 2 oxygens on the left. Right-hand side, 1 nitrogen. We have our 6 hydrogens. We now have 1 oxygen there and 3 times 1, which is 4 there. And that gives us a grand total of 4. So we fixed hydrogen, but really messed up everything else. And once again here, to me, the easiest thing to fix at this point is going to be the nitrogen, as it's only in one spot on each side. We got oxygen in a few places there. So to fix the nitrogen at this point, we're going to put a 2. And again, that's going to go to everybody behind it. So that's going to give me 2 nitrogens. Hydrogens will still be 6, as this also gets distributed to both. And in terms of oxygen now, we do have 2 there, and we have 3 there, which is 5 at this point. So again, we come to the situation, pretty much the only thing we have left to sort of do is the oxygen. We basically have 2 on one side, 5 on the other. So this is a good way to use a fraction here to get us what we need. Once again, in terms of the fraction, the number that should go up on top is the number we need. So in this case, we need 5. And on the bottom should match this guy. So it cancels. So that is a 2. And if we do that, we will end up with 2 nitrogens, 6 hydrogens. And once again, when we take 5 over 2 times 2, the 2's cancel and give us 5 oxygens. At this point, this is technically balanced, but we cannot leave it like this because we cannot leave a fraction or a decimal or anything like that. So we do need to actually clear the fraction by multiplying by the denominator. And again, we're going to multiply everybody by that denominator, and that's going to get us 4NH3 plus 5O2, 4NO, and 6H2O here. And at this point, we should still be balanced. We have 4 nitrogens. We have 4. We got 4 times 3, which is 12 hydrogens. And 6 times 2 is 12. And 5 times 2 is 10. And we have 4 here, oxygens, and 6 more make 10. And we are balanced. Any question on that one there? So again, like I said before, this oftentimes does happen when you do have perhaps like a diatomic element on one side and that element and a couple of things on the other side. So sometimes a fraction is kind of the best way to do it, unless you can see kind of the larger numbers to balance it. Then you can obviously do it that way as well. Any questions on that there? All right, last 2 here, maybe to balance, try these 2 out and see what you come up with. Okay, so let's take a look at this. So when we look at these 2 equations here, we want to balance it. You could obviously do what we've been doing previously, which is make a table of all the elements. Now, one reason you might not want to do that is we do see a lot of polyatomic ions in here. And we see polyatomic ions that look the same on both sides of the arrow. And whenever you sort of have that situation where you got some polyatomic ions on both sides of the arrow, a lot of times it's easier when you're balancing the equation to just keep them together and balance them as like whole units rather than go sort of element by element. You can go element by element, but sometimes with polyatomic ions, because you got parentheses, you got a lot of kind of multiplying in and multiplying out. So if you take an approach, it's sometimes a lot faster just kind of keep them together. In the case of the top one here, we have carbonate on both sides, CO3, and we have phosphate on both sides. In this case, we have one CO3 on each side, so I'm not going to play with that. But we do have two phosphates on the left and only one on the right. And that's where I would start. I would just put a 2 here to balance out the phosphates. Now, when you sort of do this method, what you want to do is, because we put the 2 to balance out the phosphate, the next place we want to go actually is whatever it's attached to, which is the sodium. So the sodium now is 6. So we want to go over to the left-hand side of sodium and make that a 6. So we need to put a 3. And when we do that, that gives it a 6. That then changes our carbonate here to 3 of them. And that's where we should go next, which is to put a 3 in front of our carbonate. That also will put a 3 in front of the iron, which is what we need. And now we have it balanced relatively quickly. So by keeping those polyatomic ions together and just kind of balancing them first as whole units, will oftentimes be a lot faster than going element by element, when we kind of did before. Any questions on that there? Now we can do kind of the same thing here with the second one. We do see sulfate. We got some sulfate happening. We also have hydroxide. And in this case, we have one sulfate on the left and 3 on the right. We also have 3 hydroxides on the left and 1 on the right. You really could start with either one. Sometimes it will work better than the other. So for example, if I did start with sulfate, I got 1 on the left and 3 on the right. So to fix that, I'm going to put a 3 there. And that's going to give me 3 sulfates. That will then tell me I should go to silver next, which I need 6 to get silver to 6. That's going to put a 6 there. That 6 then will tell me that I now need 6 hydroxides. And to do that, I will need a 2. And that needs the 2 that I need for the chromium. And I'm balanced at this point. So as you can see, it's relatively quickly to do that. As I mentioned, you could start with either one. And again, sometimes it may work out better than the other. It may not work out so great, but let's just see. So for example, in this one here, bless you, if I started with the hydroxide and I said, okay, I got 3 here and only 1 here, and I put a 3 here, that does balance the hydroxide. And then I would go to the silver, which would need 3, and I could clearly see I already have 2, so that's not going to work so well. But what I can do at this point is go, all right, I have 3 silvers on the right for the hydroxide, and I have 2 on the left, so the common number is 3 times 2, which means I need silver to actually be 6. And you could kind of quickly change it, or you could go to the other polyatomic ion and do it. And then at that point, you could kind of roll through with your normal sort of balancing that would happen in this particular case as well. So as you can see here, there are a couple of ways of doing it, but definitely if you have polyatomic ions on both sides of the arrow, it's best to kind of keep them together, balance them as whole units. Any question on any type of balancing? So pretty much if you're using an equation in chemistry, you need to make sure it's balanced. And if it's given to you balanced, you're good. If it's not given to you balanced, then obviously you should look at it. And I would say that if you see coefficients, it's probably balanced, but you should always take a look at it. If you don't see any coefficients in an equation, you definitely should take a hard look at it. All right, so for the rest of sort of what we're going to talk about in this chapters here are really types of reactions and ways to classify reactions. And as we'll talk about it, there's really kind of 2 main categories of reactions. There are double displacement reactions. And there pretty much is a big category of what are known as redox reactions. And when we look at a reaction and why a reaction takes place, there's pretty much 3 main reasons why a reaction will take place. And basically boil down to these 3 reasons. One is a precipitate or solid is formed. One is water is formed. and third is a transfer of electrons. So pretty much most all reactions that you come across in chemistry will pretty much boil down to one of these things, three things happening, which is why that reaction is really taking place. These are sometimes referred to as the driving force for a chemical reaction, is one of these three things sort of happening. And when we look at reactions, as we will see in the rest of this lecture, they basically reactions can be classified in multiple ways. So you can look at the same reaction and classify it many different ways. But most all reactions fall under one of these big categories, as I mentioned before, which is double displacement or redox reactions. So double displacement reactions typically take care of the first two things: is either you make a precipitate or you make water. So a double displacement reaction ultimately will result in one of those things happening. Either you made a solid or you made water. Redox reactions, as we will talk about, will take care of the third reason, which is a transfer of electrons. So these two big categories of types of reactions are basically take care of the three main reasons why reactions take place. And underneath these two big categories of reactions, we will talk about more specific ways that you can classify reactions. But ultimately, they kind of fall into these big umbrellas. Either they're going to be a double displacement reaction or they're going to be a redox reaction. Any questions on that there? Okay, so let's get into some of the things, and really we're going to kind of start with double displacement reactions here. But before we do that, let's talk a little about electrolytes. And electrolytes are substances that, when they dissolve in water, will result in basically the solution that conduct electricity. A non-electrolyte is a substance that, when dissolved, will basically not conduct electricity. So when we talk about electrolytes, there are strong electrolytes, and strong electrolytes will 100% break apart into ions. So for example, if you had a sodium chloride solution, what you really have in that beaker is 100% sodium ions floating around, chloride ions floating around inside that beaker. Pretty much that's all you got kind of floating around in there. You will have none of these units still together. It will completely dissociate into ions, and really the only thing you'll have floating around are those ions surrounded by water, basically, but they'll basically floating around. And it's the presence of all these ions that help really connect and complete the circuit and help it conduct electricity really, really well. So a strong electrolyte will basically produce a bunch of ions really quickly, and that will make very common examples like a light bulb. You take like a light bulb that has some electrodes attached to it and put it into a strong electrolyte solution, it would go off very bright. So your light bulb will kind of turn on. It'll be very, very bright. There's a lot of ions floating around, and that's going to help conduct electricity really, really well. And it's basically a one-way street when we talk about a strong electrolyte completely going to break apart. Most ionic compounds, when they're dissolved in water, are strong electrolytes, because pretty much that's what you have. It's just these ions basically floating around. Strong acids, strong bases are also strong electrolytes because they completely break apart. So if you had something like hydrochloric acid, which we used the other day, or even nitric acid that we also use, when you have or use hydrochloric acid or nitric acid, when you use that, it basically is nothing but H pluses and Cl minuses floating around. And it is, again, 100% these ions in solution. That's why it's considered a strong acid, because it has the ability basically to produce a bunch of H plus really, really quickly. And that's the definition of an acid, is something that has the ability to produce that H plus. So that's why it's considered a strong acid. And also, in addition to being really strong, will also conduct electricity really, really well. Now, if we take something that is a weak electrolyte, it will still break apart, but it will mainly stay together. But it will break apart into a few ions in solution. So if you take something like hydrofluoric acid, which is actually a weak acid, and you put that into solution, it will break apart into H plus and F minus. The difference, though, between, say, hydrofluoric acid and hydrochloric acid is what you have in solution is mainly the HF units still together. So mainly what you have floating around in that solution is HF still together. You have a little of these guys floating around. So for example, if you were to look at like the beaker view of what's going on with that, and you throw it in there, it's mainly going to be HF basically floating around. But you will have a little bit of H plus by itself, a little bit of F minus sort of floating around. So because it's still able to break apart a little bit, it's still able to produce a little bit of ions in the solution, it still can conduct electricity because the presence of ions are there still. So with a weak electrolyte, it will still produce a little bit of ions, but nowhere near what a strong electrolyte will do. So in terms of our light bulb example, it will go off if you kind of put that little electrode with the light bulb in there, and it will go off, but it'll be very dim, almost like it's dying, but it will kind of light up a little bit. And again, it's because it is mainly has some ions present in the solution. Any questions on that there? Also, different in terms of sort of a strong electrolyte and a weak electrolyte are these arrows, right? So in a strong electrolyte, as I mentioned, it pretty much you can think of it as like a one-way street. Everybody's going to dump off to the product side, which means they're all going to break apart into ions. You got everybody breaking apart. Nobody's going back the other way. Different in a weak electrolyte is you often see these arrows heading in both directions. And that implies that this type of reaction is actually a reversible reaction. So when you see an equation where you see these arrows heading in both directions, this is what is known as a reversible reaction, also known as pretty much everything you talk about in Chem 200B. But in a reversible reaction, you basically have two directions. You have what is referred to as going from the reactants to the products. That is known as the forward direction. But what happens in these type of reactions is as you start to create some products and you get enough products sort of created, those products will actually start reacting with themselves and they will actually head back the other way. So you get this kind of reverse reaction that occurs as it goes from products back to reactants. And that is what is sometimes referred to as the reverse direction. And what usually happens in these type of reactions is it reaches what is sometimes referred to as chemical equilibrium. And chemical equilibrium doesn't mean that you have the same amount on both sides of the arrow. What it's actually talking about is the rate at which it goes one way and the other way. And what that means is the rate of the forward direction will equal the rate of the reverse direction. So just as quick as it sort of breaks apart, it's just going to head back the other way and remake what it broke apart. And what that essentially will do is, again, not necessarily mean that you have the same amount on both sides, but it will essentially lock everybody into place in terms of where they're at in their concentration. Because just as quick as you lose something, it comes back the other way just as quick. So everybody just gets locked into wherever they are at that particular point. So reversible reactions is typically what we see. It is kind of like a two-way street, but it is mainly hanging out here on the reactant side in a lot of cases, and you have a lot more reactants in the solution. Now, a non-electrolyte is something that will dissolve, but not produce any ions. So for example, if you take sugar, which is basically carbon, hydrogen, oxygen, all nonmetals, will dissolve in water, as we know, and we will get sugar in water. But because these guys are covalently bonded, when you put that into solution, you basically just get sugar molecules floating around. You get no ions. And because of that, the presence of no ions really, it will not conduct electricity. So if you do that little experiment with the light bulb, it will basically not turn on because there are no ions present for it to turn on. So strong electrolytes, weak electrolytes, and non-electrolytes, mainly strong electrolytes and weak electrolytes, are really important in certain types of reactions that we're going to talk about, specifically double displacement reactions in terms of what is happening in that case. By the way, if you have pure water, is it a good conductor of electricity? Pure water is actually a bad conductor of electricity because there's no ions. If you have pure water, it's just H2O molecules floating around, covalently bonded to each other. Safety note, clearly the water that comes out of your shower and so forth is not pure water. They actually put ions into the water to purify it. And there's a lot of ions in there, which is why they tell you not to blow dry your hair, right? Or listen to the radio in those showers so you don't get electrocuted, because you will get electrocuted because the water coming out of your faucets are not pure water. There's lots of ions in there, which is why they will conduct electricity really, really well. Any questions on that? So as I mentioned before, here's sort of the example, non-electrolyte. As you can see, if you took a light bulb, because there's really no ions present in that solution, will not basically turn on. Here is a weak electrolyte. Again, we got a little bit of ions floating around in here. You can see the light bulb will be able to kind of turn on, but it's going to be very, very dim. And if we get to our strong electrolyte where we have a ton of ions basically floating around in the solution, you again can see it can conduct electricity really, really well. And the light bulb will go on very, very brightly because it is conducting those electricity. So as we just talked about there, we have our strong electrolytes. Again, most ionic compounds, when they're dissolved in water, are strong electrolytes. Are just going to pretty much break apart into ions and will conduct electricity. Our weak electrolyte, again here, with our arrows heading in both directions, that's acetic acid or vinegar, basically, major component of vinegar. It's acetic acid, which is also a weak electrolyte. A lot of weak electrolytes are weak acids and weak bases, like hydrofluoric acid, acetic acid, hydrocyanic acid. There's a lot of carbonic acid. There's a lot of acids that are sort of weak acids and weak bases, like ammonia, for example, is also a weak base. These are guys that are typically your weak electrolytes. Again, your strong electrolytes are usually anything that's sort of ionic is definitely usually a strong electrolyte. And again, those arrows are a big hint that you're dealing with that weak electrolyte. So in the case of acetic acid, we would expect in a solution of acetic acid to pretty much have mainly the acetic acid guys still floating around. But again, because it's able to produce a little bit of the ions, it is still going to be an electrolyte. And again, why it's a weak acid? Because it was able to produce a little bit of H+. When ions do go into solution, they are hydrated. And what that means is, as we know, water is a polar molecule where the oxygen is more negative and the hydrogen side of water is more positive. And that works really well when you want to go dissolve something in water. So if you took something like sodium chloride, which is basically going to be sodium ions and chloride ions, what happens is the positive sodium ion will get surrounded by water, but it would get surrounded by the negative side of water, which is the oxygen side of water. Same thing will happen with our chloride, but because chloride is negative, it would also get surrounded by water, but it would get surrounded by the positive side of water, which is actually the hydrogen side. And this is actually how something gets dissolved. Basically, before you dissolve an ionic substance, it's in a nicely organized, badly drawn here, ionic sort of situation where all the ions are clumped together basically with each other. And what happens is water molecules come and basically pluck off each of these ions, and then they get surrounded. That is helped along by when you usually go to dissolve something in water, you oftentimes will take something and start stirring it, right? So when you stir it, you put a bunch of water molecules all over the solid. You also provide some energy, and that allows each of these ions to get plucked off, get surrounded by water. That's also why when you dissolve something in water and you make a solution, it is a homogeneous mixture. It is a physical change because the substance is still there. And you know that, like when you evaporate off salt water, you'll get your salt back, right? And just kind of similar to what you did the other day when you evaporated off the thing in the water bath in your evaporating dish, right? You had all this liquid and water aspect of it. You evaporated off all the water, and back came sort of your ionic solid that came back as sort of a solid. So the water does two things when you dissolve something in it. There's a super strong attraction between the positive ion and negative ion. When they have nothing in their way, they definitely want to just come together and make that solid. But the water basically prevents them from coming back together. But when you do heat it up, for example, all the water molecules evaporate off. And basically, there's nothing to stop these two guys from coming back together. And that's why you'll see your solid basically return if you evaporate off, the water part of, say, salt water in a process like that. Any questions on that? So non-electrolytes, as I mentioned, will not have any type of ions present, will not conduct electricity. Here's a table. You probably have a similar in your book, but again, as I mentioned, strong electrolytes, a lot of strong acids. These are some strong bases, and ionic compounds are definitely strong electrolytes. A lot of weak electrolytes, as I mentioned, is really some weak acids. That's acetic acid, hydrofluoric acid, nitrous acid, weak base like ammonia, and water in a sense as well. Non-electrolytes, again, these are all sort of non-metal things that are covalently bonded, but sugar will dissolve, methanol and those type of things. But when they do dissolve, they do not break apart into any ions, again, because there's really non-metals and non-metals covalently bonded together. So again, no conducting electricity. So let's talk a little about solubility, which is also, in addition to sort of electrolytes and strong electrolytes, weak electrolytes, also really important in what's happening in, say, double displacement reactions. And solubility is the maximum amount of a solute that will dissolve in a given solvent at a specific temperature. There is a limit to solubility, so even things that are soluble, there is a limit based on temperature and how much, say, water or whatever you may want to use to dissolve it in, that it will dissolve. So if you take some sugar packets, for example, and you just take a couple of sugar packets and some water, it will definitely dissolve. But even though sugar will dissolve in that aspect, if you took that same glass of water and took like the Costco sized bottle of sugar and just dumped it all in there, at some point you won't be able to get all that sugar to dissolve, and it will basically dump off. So typically speaking, when we dissolve something like a solid in a liquid, increasing the temperature oftentimes will increase the solubility of something, and decreasing the temperature oftentimes lower the solubility of a lot of things. So one type of reaction that's important is a precipitation reaction, and this falls under our double displacement reactions. And the general trend in double displacement reactions is we have two ionic compounds. So that's kind of how you know you're dealing with a double displacement reaction. You got two ionic compounds. And whenever you have two ionic compounds together, a positive negative guy and a positive and negative guy that's come together, they always happen this way. The two positive guys basically switch partners. So the two positive guys will switch partners. It will form two new ionic compounds on the product side. And the result of this is one of these guys will form a solid, hence the name precipitation reaction. And a precipitate is an insoluble solid that forms kind of similar to that experiment. Maybe we did experiment 3 where you put them together and you're looking for some type of solid that will form. Remember that a solid doesn't have to be like a rock hard solid. It could be, again, it gets cloudy, stuff floating around that wasn't there before. So a precipitate like we see here. And if we look at this reaction, this is lead 2 nitrate plus a little sodium iodide will form lead 2 iodide and sodium sulfate, sodium nitrate, not sulfate. And this is what is referred to obviously as our molecular equation. And we do get a precipitate that forms in this particular case. By the way, I know this is going to be a double displacement reaction because this is an ionic guy and this is an ionic guy. And again, they're just going to switch partners when they go to the other side. And we can see that the lead ends up with the I, and our other two guys switch partners as well. Our sodium and our nitrate come together here to make our sodium nitrate. So we get this double sort of switch that occurs. By the way, when we predict something like this, for example, lead-2 and sodium iodide. Let's just say we had something like this, for example, and we had to predict what goes on the other side. Again, when we look at this and we want to put it together, we know that they're going to switch partners. And when you do this, it's really important to just think about the basic ions that make up both of these things. So the basic ion for this guy is lead with a +2 charge, even though there are two nitrates here. The formula for nitrate is just this. And those are the basic two ions that make that guy up. Same thing here. That is sodium, which is group 1, is +1. And that is iodide, which is group 7, which is -1. So when you have to like predict what goes on like the product side on this side, it is important just to think about the basic things and then put them together like you were doing nomenclature, which means when I put +2 and -1 together, that is what I should get in terms of my formula to balance it out. And when I put sodium, which is +1, and nitrate, which is -1, I get NaNO3, which is the proper formula. I do not get Na like NaNO3 or anything like that. So again, very common people, if they have to sort of predict what's on the product side, will try to balance and write formulas first, and you don't want to do that. You just want to put them together properly. Now I should look at the balancing part of it, and I see that I am not balanced, but I do see a polyatomic ion on the left and right, and there's two nitrates on the left and one on the right, so I can put a 2 there, which means I do need to go to sodium and put a 2 there, and now I have a balance. So this is what I was talking about earlier when we were talking about balancing equations and predicting formulas. It's really important to start first with the proper formulas, regardless of the balancing aspect of it. You just want to put it together properly based on charges and like you're doing with nomenclature. Once you have the proper formulas together, then you want to balance it. I can't tell you how many times I've seen people write Na2NO3 and all these kind of weird things like sodium chloride ends up as Na2Cl2 because they're trying to balance and write formulas at the same time. So best piece of advice, if you have to predict what's on the right-hand side, just think about if it's ionic on both of these, basic ions of each of those, and then put them together correctly to balance out the charge to 0. And then you should balance it after you have all the proper formulas together. Any questions on that there? Okay. So now that we have this, this is our molecular equation. This equation does describe sort of what is happening overall with all the formulas together in their proper sort of units. But it doesn't really adequately describe sort of what is happening when you look at sort of the beaker. If you look at a beaker, you're going to throw all these things into. You're basically going to be tossing in these ions we just talked about. You know, we got some nitrate with some lead, some sodium, and some iodine. So these guys are going to basically go for a swim. So we can write an equation that describes sort of what is happening when we kind of mix all these together. And when we do this, anything that is a strong electrolyte will 100% break apart into ions. Anything that's a weak electrolyte will stay together. Anything that is like a solid, liquid, or gas will basically stay together. Otherwise, they wouldn't be a solid, liquid, or gas in most cases. So when we look at lead-2 nitrate, that is a ionic compound and also a strong electrolyte. So just clear that so you can see it. we're going to break this guy apart, and that means that we will have a lead with a +2 charge, and it's aqueous. This 2 for the nitrate actually comes in front because that means we have 2 nitrate ions floating around basically in that solution. The sodium iodide is also a strong electrolyte, which means it will break apart, and that 2 in front gets distributed to everybody behind it. So that 2 means we have 2 sodium ions and 2 iodide ions. Now over here, we do have our precipitate, which is a solid, and the only way for that precipitate to be a solid is those guys have to come together and stay together when they find each other, basically. So that will stay together. We do not break it apart. So again, anything that's typically a solid, anything that's a pure liquid or gas or a weak electrolyte will stay together. Now, this sodium nitrate is also a strong electrolyte. So I'm running out of room, so I'm going to go underneath it. So 2Na plus as we distribute the 2 and 2 nitrates as well. This is what is known as the total ionic equation, or some people call it the complete ionic equation. When you write a total ionic equation and you write formulas for ions, because they are ions, they need charges, yes? So anything that's an ion in a formula will need a charge. So you do have to put like the +2s, the -1s, and the +1s and stuff like that. When we look at the total ionic equation, which basically describes what happens when we kind of dump everything in together, we also can look at it and we should be able to find ions on both sides of the arrow which look identical to each other. So for example, we have 2 sodium ions and 2 sodium ions on the right. We also have 2 nitrate ions on the left and 2 nitrate ions on the right-hand side. They are exactly the same. You have the exact same amount of those ions. And by the way, if you don't have the exact same amount of those ions, you probably screwed up in your balancing part of it, just so you know. These guys are what are referred to as spectator ions. If you are a spectator, you are essentially just watching, and that's essentially what's happening here in this reaction. These guys are in the solution. They're not really doing anything in terms of product being formed. They're just floating around to balance out charges. So when we have spectator ions, we basically can cancel them out on both sides of the arrow, and they should completely cancel out. And that will leave us a third type of equation, which in this example will be PB2 plus our 2I minuses will form our PBI2. And this is what is known as the net ionic equation. The net ionic equation pretty much tells you exactly what is happening in this reaction. What is actually happening in this reaction is the lead ions from the lead-2 nitrate are going to find the iodide ions from the sodium iodide, and they're going to come together basically and make this solid. So the actual reaction that's happening is this guy here and this guy here are going to come together to make that yellow solid there. And that's ultimately what's happening here. That is the precipitate that's being made. That is a double displacement reaction. And that is one of the 3 reasons why a reaction takes place is really the formation of a solid, which is what we see here. Any questions on that? So also in the net ionic equation, again, the ions do have charges. So a very common mistake people make is when they write a total ionic equation or a net ionic equation for ions, they do not include the charges. You do need to include the charges, and everything needs to be balanced when you do that. Any questions on any of that? So how do we know if we mix things together, will we get a solid or will we not get a solid? And that is basically what are known as solubility rules. And here are some of the solubility rules. And if we mix something together and they are soluble, that means we would not expect a solid to form. they will get the aqueous symbol next to them. So the aqueous symbol goes to anything where, based on solubility rules, it means that they are soluble. It means pretty much no solid is going to form, just everybody's going to float around basically in the solution. Now, if you mix things together and you do get a solid that forms, that is what is known as being insoluble. And those are guys that get the solid symbol next to them. And there are certain rules here which we see, and these are the general solubility rules for things in water. Anybody essentially in group 1 on the periodic table and ammonia are always going to be soluble. So that means that if you have a formula where you see any of those guys in it, pretty much they're going to be aqueous, no solid is going to form, everybody's just going to be floating around in the solution, kind of free as ions in there. There are no exceptions on the right-hand side here, which means as soon as you see it, it doesn't matter what's attached to, it's always going to be soluble. Same thing here, if you have something with nitrate or acetate in it, there are no exceptions. So as soon as you see that in a formula, you know 100% of the time it's going to be aqueous. You're not going to expect any type of solid that forms. In addition, if you have chloride, bromide, or iodide, those guys are also going to be soluble. But in this case, there are some exceptions. And the 3 exceptions are if it's hooked up with silver, that is mercury 1, by the way, and lead 2. So if you have silver, mercury 1, or lead 2, that is going to be the opposite of being soluble, which means they will be insoluble and will form a solid. So if you have sodium chloride, that's going to be aqueous because that's sodium. But if you have something like lead 2 chloride, it will be insoluble, it will be a solid, and you would expect to precipitate the form. Now, if you have something like sulfate in a formula, it will be soluble. But again, there are some exceptions like silver, calcium, strontium, barium, and lead. And if you hit one of those exceptions, we would expect a solid to form. So again, there are some exceptions. Any questions on those there? Now, there's also some rules for things that are typically insoluble. So if you look at this, these are typically things that are insoluble. So these are typically things that will form solids when they are in the formula. Hydroxide will typically be solids, except though, basically the exception that we just talked about, if you have somebody in group 1 or ammonium, they're going to be soluble and aqueous. These guys are going to be what are considered slightly soluble. For the most part, most people consider slightly soluble to be more towards insoluble than soluble. But slightly soluble is pretty much what the name sounds like. It does have a little bit of solubility, but mostly of it is not. Most of it is not going to dissolve. Basically, it's going to be more insoluble and stuff. Anything with sulfide will be a solid. But again, there are some exceptions, and the exceptions, once again, is pretty much group 1 and ammonium. And also calcium, strontium, and barium are some exceptions to that as well. Those guys then would be aqueous, and you wouldn't expect a solid to form. Lastly, if you have carbonate or phosphate involved there, going to be a solid. Once again, though, the same sort of general exception, which is group 1 and ammonium, will be aqueous. So most of the exceptions on these guys are pretty much the first rule right here, that they're going to be soluble. So they kind of go together in terms of the exceptions. So if you remember sort of this, you probably don't have to worry about the exceptions on the other side, because that's mainly what those exceptions are. So how do we use these? Like, so for example, if we had some sodium nitrate plus some actually no, let's do some sodium. Let's do some sodium chloride plus some silver nitrate. And we end up with some sodium nitrate and some silver chloride. Okay, so let's take a look. So we're going to look at the first one here, and really I see sodium, and that is group 1, and there are no exceptions. So really you don't have to go any further than that because there are no exceptions. We do know that this guy is going to be aqueous in this particular case. If you wanted to, you could go to chloride, which is down here, and you see the chloride soluble in everything except for silver, mercury, and lead, which is not the case here, so it also will tell you the same thing. I come over here to silver, which I might not see, but I do see nitrate as one of the guys here. And nitrate is soluble pretty much in everything. There are no exceptions, which means that's pretty much all I need to know. And those two should be aqueous. Once again, here on the right-hand side, I come to sodium, which again is our first one here, and there are no exceptions, which means I do not even really need to look any further. I know it's going to be aqueous and soluble. I could also, again, look at the nitrate, which obviously has the same rules there. Now I look at silver, but I do see chloride here. Chloride is soluble in everything except for silver, which is one of the exceptions. So instead of being soluble, it's going to be the opposite, and we would expect that to be our solid in this case, and that would be the white solid that would form when you would mix these together. You might have done it the other day. I don't remember in one of those experiments. Any questions on that there? All right, so why don't you try one more here? Why don't you try what happens? Why don't you write the rest of the equation and balance it? So let's do a little barium nitrate plus some sodium sulfate. So balance the equation, predict what you get on the other side, and then use the solubility rule to decide are they soluble or insoluble. Okay, so let's take a look. So once again, when you look at this, the first thing that should jump out at you is this is an ionic compound, positive negative guy. That's an ionic compound, which is a positive negative guy. So we do know that our two positive guys are going to switch partners here. We do want to think about this, as I mentioned before, is really the basic units first. So that's barium that has a +2 charge, and that is nitrate that has a -1 charge. Those are the basic two units of what makes barium nitrate. Over here, sodium sulfate, Na plus and SO4 2 minus are the two ions that make up this guy. It is again important to put this together first correctly before you try to do any balancing. So if I'm going to put these together, Ba is +2, SO4 2 minus is -2. That gives me BaSO4 as the correct formula. Sodium is +1, nitrate is -1, which means I again should get NaNO3, not Na2NO3 or anything like that. Any questions on that there? Now that I have the correct formulas, now I should be concerned with the balancing, and we're not balanced. So again, we still have some polyatomic ions now on both sides. I can see the nitrate 2 on the left and only 1 on the right, so I could put a 2 there. That also means I need a 2 for my sodium there, which I already have. And now I have the balanced equation. So again, I can't stress enough, that is the order at which you should do this, correct formulas, and then balance. Don't try to do it together. Otherwise, you will get the wrong sort of formulas and the wrong equation. Any questions first off on that there? Now that we have our correct equation, we want to use our solubility rules here to basically determine solubility. So barium nitrate, it's really the nitrate there. As soon as I see that, tells me it's going to be soluble. There are no exceptions, so that should be aqueous. Sodium, as soon as I see the sodium, I know it's going to be soluble because there's no exceptions. So I know that this guy will also be aqueous and soluble. I could also look at sulfate, which again is soluble in everything except for silver, calcium, strontium, barium, or lead. And in this case, again, it's with sodium, so it's going to be soluble. Now coming to sulfate, though, we do have sulfate that is attached to barium, and normally sulfate is going to be aqueous, but with that exception, that's going to tell me we're going to get a solid here, a barium sulfate. And for the last guy there, sodium sulfate, sodium nitrate, the sodium or the nitrate will both tell you that it's going to be aqueous. Yeah. So our solid here, which is going to make this a precipitation reaction, is going to be the formation here of our barium sulfate. First off, any questions on that? Now, again, we could really see what's going on in this case, which is when this thing breaks apart, we will have our barium with a +2 charge. We will have our two nitrates that's going to break apart. We will have our two sodiums, that's a strong electrolyte, and our sulfate that will break apart. We will have our barium sulfate stay together because it is a solid. And again, this is a strong electrolyte, which will break apart. So I'm just going to go underneath because I'm running out of room again. So two sodiums and two nitrates in this case. And this would be our total ionic equation. And we again can see that the nitrates and the sodium are spectator ions, which will cancel out and leave us what's really happening here when we mix these two things together, which is the barium ion will go find the sulfate ion, and they will come together to make this solid of barium sulfate, which is our net ionic equation, which is really what's going on in this case. And once again, the formation of that solid, really the reason why this reaction is taking place. Any questions on that there? Yeah. If it's a gas or a liquid, it would also stay together. You would keep it together. So when you get to the total ionic equation and even the net ionic equation, but really the total ionic equation, if you come across anything in your original equation that is a weak electrolyte, it will basically stay together. It's a solid, liquid, or gas for most parts. Those will typically stay together as well. It will not break apart. Everything else will pretty much break apart. Anything that's ionic, for most part, is going to break apart. That's aqueous. So really, those are the kind of the things you just have to worry about. I would say in our class, in most cases, probably it's going to be the weak electrolyte or something that's solid or liquid. But there will be some gases that pop up as well that stay together. Other questions? All right, we're laid up there for now.